All right, so now we're looking at, yes, what did we look at on Friday? What did we talk about? We were talking about intermolecular forces and then leading into types of solids, right? And we connected intermolecular forces to things like melting point and boiling point. So let's talk a little bit about vapor pressure. Don't let it scare you. It's so easy. When I ask people about vapor pressure, it's like, oh my God, what is it? Super simple. If you have a closed container, okay, can you see stuff? Yeah. And you have a liquid in the closed container. The liquid, a small portion of it, especially the molecules at the surface of the liquid, are going to be in equilibrium from gas above the surface into liquid, back and forth and back and forth. So this gas above will hit the walls and will bump into each other. And what is it called when things hit the walls and bump into each other? That's pressure. Since it's pressure of the vapor above the liquid, what do we call it? Vapor pressure. Okay? Don't let it scare you. It's nothing you don't already know about. Okay? It's just pressure of these gas molecules above. Now, what I want to do is correlate this vapor pressure to the intermolecular forces found in this liquid. Let's say we have hydrogen bonding intermolecular force in the liquid versus London dispersion. Which one of these, okay, so hydrogen bonding, we know, are molecules more attracted to each other or less? More. So what can you tell me about the number of molecules that would then be in gas phase if we had hydrogen bonding? Less. So what would you tell me about the vapor pressure? Lower vapor pressure because less molecules would be in the vapor phase. Versus London dispersion forces, we'd have a higher vapor pressure. London dispersion forces then are going to, it's like all the stinky stuff. If you walk by perfume, you can smell it. Sulfur, low LD forces will allow more into the vapor phase, and when you smell, that's what you're smelling. You're smelling gases. So London dispersion forces are present in substances that have very high vapor pressures. Got it? Okay, so this is a table just basically proving that to you. I'm going to pick a low temperature like, I don't know, 30. Okay, look at that. That's a straight line. So if you look, we've got very high vapor pressure for this guy and lower ones for these. And let's talk about why. You might not, and I'm not going to hold you accountable for it right now, but does anybody remember what type of molecule this is? We have a C2H5, and then we have an O in the middle, and then another C2H5 on the other side. Close, not an ester, ether. Very good. So we're going to revisit the organic molecules later, but I just want to show you this particular molecule. A lot of students want to say it's polar, but it's really not, because this poor little electronegative O is like surrounded by a whole bunch of nonpolar hydrocarbon chains. So this molecule is essentially nonpolar. If it's a nonpolar molecule, what are the intermolecular forces within it, within the substance? London dispersion. Okay, that's why it has such a high vapor pressure. Those molecules don't want to be around each other much, so it more easily goes into the vapor phase. Now, what about this? We know C2H5. Not that you know anything about these substances. What is this one called? What specific alcohol is this? Yep, ethanol. Okay, ethanol is polar or nonpolar? Polar. And what type of London dispersion forces with this one? Not dipole. Hydrogen. Isn't hydrogen attached to an NO or an F? Yep, so this is hydrogen bonding. We know what water looks like. Is water polar or nonpolar? Polar. And I just want to draw it because we're going to have to talk about this. So this is polar. So what's this intermolecular force? Hydrogen bonding as well. So the question I have for you is why does water have a lower vapor pressure than ethanol? That means that its hydrogen bonding must be stronger. Anyone want to tell me why? Any ideas? Okay, the reason this is going to be a bit stronger in its intermolecular force is mainly because of the shape and the ability for multiple sites of hydrogen bonding. You see how we have a partial positive here? I can have a partial negative of another one come in there and in there, and so on and so on and so on. So we have more sites, and the bent molecule allows for that type of compaction to happen. Here, compaction, is that a word? No, okay. It is now. What's the date? Mark this. November 21st, 133, compaction, new word, copyright, DiMartino. No, compacting. Compaction. I'm taking compacting and putting it in noun form. If you look at this molecule here, this is a molecule that's got a whole bunch of nonpolar stuff around it, and there's not going to be as many sites that we can get this partial negative and positive to attract. Here we're going to get the partial positive, the big fat part of another molecule come in, and you see how there's not as much networking going on. Okay, so this is going to be a stronger intermolecular force. That's why it's got a lower vapor pressure. I made the biggest mess of this page ever. That's okay. Questions on this? All right, moving on. Important. Boiling point is the temperature at which the vapor pressure of the liquid equals the atmospheric pressure. I want you to know this definition. Let's see if this makes sense. I have a container with liquid in it. When it boils, the vapor pressure has to equal, that's the pressure that's going to be basically of this gas when it evaporates, has to be equal to the atmospheric pressure pushing down, right? At that exact moment, that's the exact point when it starts to boil. And then if we increase the temperature, is it still going to boil? Yeah, it goes beyond at that point. But right at that exact, it's like a balancing act, a little equilibrium. So I need you to know that's the textbook definition of boiling point. So it kind of makes sense? When the atmospheric pressure equals the vapor pressure. Another term I need you to know is normal. If you see the word normal, and we want to know the normal boiling point of something, we're referring to standard pressure. So the normal boiling point of something is going to be at the boiling point, or the temperature at which boiling occurs at 1 atmosphere. So what's going to be new, and I do not want you to memorize this, is this equation called the Clausius-Clapeyron equation. And this Clausius-Clapeyron equation is going to give us the opportunity to find the heat of vaporization of a substance. What is the heat of vaporization of the substance? What does that mean? Heat of vaporization. The heat at which something vaporizes. So that's kind of how much heat's required to boil something. To do this, there is a relationship between the pressures and the temperatures. So what this is used for, this Clausius-Clapeyron equation, if you have a substance and we find the substance's temperature and pressure, different combinations, we find its pressure at one temperature, we increase the temperature, find its pressure, and so on and so forth, we can figure out what the heat of vaporization is. And that's strictly what you're going to use it for. This is kind of above and beyond the AP in that you won't be tested directly on the memorization of the formula. But one thing I do want you to know is how to use the formula in a graph. Let's go ahead and first talk about the formula, and then I'll talk about graphing. So P1 and P2 are the pressures of the substances. And we're testing at different pressures and temperatures. And T1 and T2 are the temperatures associated with those pressures. So it's like two ordered pairs. We take something, heat it up, find its pressure. We heat it up some more, or cool it down, whatever, get a different temperature and find its pressure. Same substance, okay? Ideal gas constant here. Why are we using 8.31? We're dealing with the heat that has to be in joules. So here we're going to get joules per mole when we use it appropriately. What does our temperature have to be in? Units of Kelvin. Does it matter what our pressure unit is? Why not? Right when you divide, it cancels out, right? So units don't matter as long as they're the same. The heat of vaporization is the amount of heat required to change 1 mole of pure liquid into 1 mole of a pure gas. So we're going to figure out what that heat is. We're going to do a lab. And the lab we're doing, and I can't decide if we're doing it online or in real life because the real life version is so bad. We're going to take I think we're going to take ethanol, and we don't get good results, and it just frustrates me. So we're going to take ethanol, we're going to take it, we're going to start it at room temperature at 25 degrees Celsius, go up to 30, 35, 40, whatever, and so on. And then we're going to measure the pressure at each one of those temperature values. What's going to happen to the pressure as we increase the temperature? Increase. Vapor pressure increases, right. And then we're going to go, and your job is to figure out the heat of vaporization of ethanol, because it's a standard value. So you're going to utilize this data to find that. How are we going to find it? Well, we're going to do some graphing. Rather than just picking 2 points and plugging them in, we're going to graphically take this equation and do what we call linearize it. It's the most popular thing chemists love to do. So y equals mx, and I don't care about whatever b that is. But look at that, y, this is the slope, and this is the x. So what the heck does that mean? What you're going to end up doing is using your calculators on the y-axis. We're going to plot all our natural logs of pressures. We're going to take those pressures, and we're going to do the natural log of them, okay, put them in one column in our calculator. And what do you think we plot on the x-axis, knowing that? Temp. 1 over temperature. When we plot, and this I want you to know by heart, if I give you that equation, I want you to know what you would have to plot to linearize it. If we were to plot that and we get a slope, our slope is equal to what? Delta H over R. So how would I solve for heat of vaporization? Multiply what? Multiply what by R? The slope by R. So if we multiply the slope times R, that's going to equal the heat of vaporization. This I do want you to know because this is what we're doing in the lab. We're going to collect a whole bunch of pressures, a whole bunch of temperatures, plot them all, and the slope is going to be that. I might give you data on the test. Again, going to give you that equation. I'm not going to keep that from you. So you can look at this and go, y is ln, x is 1 over. That's all you need to know. But the problems we're going to do, we're going to just do 2 points. The lab is for multiple points. So let's turn to the next page and apply the 2 points to each of these. So let me rewrite the equation on this page. It's ln, make sure I get my numbers right. P1 over P2 is equal to delta H of vaporization over R times, it's T2 minus 1? Okay. So now what we're going to do, here's where students make tons of mistakes, so I need y'all to get your calculators out. They're messing up their pairings of their P's and their T's. It seems simple, but we had to redo this like 7 times in first period. So we're calculating the vapor pressure at negative 45 degrees Celsius. So we're looking for pressure at this temperature. To make my life easy, since the pressure is the unknown, I want to make the unknown on the numerator because it's just easier to solve. So I'm going to make this P1 and T1. That makes this P2, and that makes that T2. Okay? I suggest really writing that up there because, again, we didn't in third period, and everybody was messing it up. So ln of P1 over my P2 I can leave in millimeters of mercury is equal to, what do I have to do to this heat of vaporization that they gave me? Change it to joules. Good, which would be what? 28,000 joules per mole divided by 8.31 joules per mole K. All right, 1 over. What do I do with my temperature? Got to convert it to Kelvin, right? So I want T2. It's 273 minus 56 minus 273 minus 45. Okay, so go ahead and solve. Okay, so the answer is 347. Is everyone good? Let's do one more. Calculate the normal. Oh, what did I say normal was? Standard pressure, 1 atm. So we have 1 atm coupled with some boiling point, because that's what we're looking for. And we're given this temperature, and we're given that pressure. So we'll call that T, whatever. I'll call it T1, P1, since solving for T2 might be easier. It doesn't matter. And then our heat of vaporization is the same as in the last problem, because it's the same substance. It's ammonia. So ln of P1, 538. You tell me what P2 is. Good. 760 equal to 28,000 joules per mole K over 8.31 joules. It's not joules per mole K. My bad. Up here is joules per mole. I had R on the brain. Okay. That times 1 minus. What's my T2? I'm looking for that, right? Minus 1 over 273 minus 38. And the answer is 241K. Now my favorite, butt diagrams. Woo! Butt diagrams. Do y'all see the butt? This is the butt. Here's our butt. I'm doing it for the video so people can see what I'm talking about. So, what comes out of the butt? Gas. Solid, liquid, gas. Okay, what a phase diagram is, every substance in the whole wide world has its own butt diagram, has its own phase diagram, and it's just a description of what phase the substance will be at any pressure and temperature combination. Okay, so let's talk about this picture. Anytime you're on a line, whatever states of matter the line is in between, both those states exist on that line. So on this line right here, solid or liquid exists in equilibrium, and that's important that you use that term. We have both solid and equilibrium, solid and liquid existing in equilibrium. Okay, what's it called the process of going from solid to liquid? Yeah, how about melting? And then liquid to solid? Freezing. And so melting point or freezing point will be the issue here, right? So the freezing point or melting point can be found somewhere on this line depending upon what pressure you're doing your experiment at, right? What's it called going from liquid to gas? Vaporization or evaporating. Okay, what about from gas to liquid? Condensation. Okay. What point is that? Not melting, but boiling point. So this is the boiling point. So anything on this line is the boiling point. It's the point at which you have both in equilibrium, liquid and gas. What's it called going from solid to gas? Sublimation. What's it called going from gas to solid? Deposition. Oh, it's right there. I am such a moron sometimes. Yeah, that's good. And then I was all proud of everyone this morning knew it was deposition. I'm like, wow, that's awesome. You learned stuff in pre-AP because it's flipping written on the paper. All right, what's this point right here? This is the triple point. And don't say anything about the butt, thanks. The triple point is where all three phases of matter exist at the same time. All three are in equilibrium of each other. If I get the chance, I don't know if it's going to happen, I can demonstrate the triple point of carbon dioxide in a pipette for you. But ultimately, all phases, and it's only at one pressure and temperature combination that can happen. Okay? All right. One thing I do want to focus on here, and this is the phase diagram for carbon dioxide specifically, is the butt crack. You see the butt crack? What's the slope of that? It's a positive slope. Pretty much everything has a positive slope there, except one thing, which we'll talk about in a minute. But what does it mean that we have a positive slope? It means that if I'm in a liquid form, okay, and I all of a sudden increase the pressure, it becomes solid. Kind of makes sense, right? Because if I've got these molecules in liquid and I start pushing closer and closer and closer together, they're going to slow down. Intermolecular forces are going to take more hold, and we're going to get a solid substance, right? Makes sense? Things get more compacted, less compactization. What was my word? I already forgot my word. Compaction. The compaction increases. I'm just kidding. And it gets more dense. And so the solids are more dense than the liquids. And that totally sounds normal, right? Water is different. Before, I kind of forgot about this point. This is called the critical point, and I'm out of calibration here. Critical point. Does anybody remember what the critical point was? No, close. Yeah, once you're at this point, regardless of how much temperature you add, or how much pressure you add, you can never get the gas to be a liquid. You're pretty much gaseous form at that point. And there's this whole thing about supercritical fluids and all. That's above and beyond what we need. You might have to read on the AP a little butt diagram and say something about it. But like I said, water is going to be a different story. So go to the next page. This is the phase diagram for water. Notice the butt crack. What's its slope? Negative. It's the only phase diagram that has a negative slope. So what happens here, as you increase pressure on a solid, it's actually going to liquefy, unlike the other way around. Water is the only substance whose solid is less dense than its liquid. Water floats, right? Okay, why is that? What's the deal with that? Water floats? What did I say? Well, solid water does float on liquid water. Solid water is whatever. Ice, which is solid water, floats on the liquid, unlike other solids which sink in its own liquid. So, stop it. Stop abusing me. The reason that happens, it's because of the bent shape of the water molecule with the strong hydrogen bonding intermolecular force. And you end up, and this is a very rudimentary drawing I'm doing, but even with this, you can pretty easily see, in order for freezing to happen and to get these molecules as close and as attracted as possible, the alignment, whoops, no, I want an H here. If you look at the alignment, what is all this here? Empty space, right? So for molecules to actually slow down enough to be a solid, they have to align in this military kind of fashion, and that's not as close as you think it could be, so there's going to be more space here, and in doing so, it causes the solid to be less dense. So this is, I always use my example of ice skating. You're really not ice skating when you ice skate. You're water skating, really, because you're wearing your skates. As you step on the ice, you're increasing the pressure. It goes to liquid, and as you skate off of it, it refreezes. Okay? So how come in big fat shoes you're falling all over the place? Any ideas? If you go out in shoes and not skates, how come you're more slippery? Less pressure. Your shoe doesn't apply enough pressure to change that ice to water. Okay, so you're really stepping on ice at that point.
You have like really heavy shoes.
I think you'd probably break the, especially if you're on a lake. No, you really need that pounds per, yeah, it's super teeny. Okay. All right. Let me pause. Okay, so let's look at this picture. It's a very disgusting butt diagram. I would be not a very attractive butt diagram, kind of a flat butt diagram. But that is, the slope is slightly negative, right? Yes? So what is this then? This is water. All right. Using the phase diagram, determine the physical state of water. This is fun. So tell me, 900 pressure and 40. This is so hard. I don't know if we can handle this. Now there's a pimple on the butt. What is that? Liquid, correct. Okay, what about 530? 530 up there. Liquid. 390. 390. Now it's just disgusting. Gas. So you're going to have more problems you need to look at in your homework as far as things you might be asked about a phase diagram. Again, the key is whenever they ask you to describe a point, say they give you this point, and they say describe what's going on there, you have to say that liquid and gas are in equilibrium. Okay? Anytime you're on a line, you've got equilibrium going on. Critical point, triple point, critical points up there. Okay? Those are the different parts you need to know. All right, das ist alles.